Hello there and welcome to Deep Sleep Discoveries. Tonight, we're drifting into the hidden architecture of the Aurora Borealis, the quiet science behind the northern lights. You may have heard the Aurora Borealis explained as a simple meeting between solar energy and polar skies, but there is much more unfolding above us than most realize. If you've ever wondered how Aurora Borealis happens, what invisible structures guide their motion, or what deeper processes shape their glow, you're in the right place. Together, we'll explore some truly fascinating facts about the Aurora Borealis, from silent electrical currents to delicate quantum transitions that turn the upper atmosphere into a living canvas. Before we begin, please let me know in the comments where you're listening in from and what topic you'd like to hear about next. Now, let your breathing slow, let the world grow quiet, and let us begin. The aurora is not simply light drifting through the sky. It is the visible edge of a vast electrical circuit that stretches from the depths of space down into the thin, whispering air above the poles. Picture a loop of invisible wire arcing from the sun, threading through the magnetic field of Earth and closing itself in the upper atmosphere where atoms glow as current passes through them. Every shimmer you see overhead is electricity completing a journey that began millions of kilometers away. The circuit runs without pause, feeding energy into the night wherever the magnetic field opens a doorway. The light is merely the place where that energy becomes visible, the way a bulb reveals the current flowing through the walls of a house. Above the aurora, the circuit continues upward into space, invisible and immense, carrying power that would overwhelm any device ever built by human hands. To watch the northern lights is to stand beneath the closing arc of a planetary power line, one that has hummed in silence since the Earth first caught the wind of its star. More than a century ago, a Norwegian scientist stood in the frozen north and imagined what no one else could see. Christian Birkeland proposed that streams of electricity flowed from the sun along invisible channels into the Earth's polar sky. His contemporaries doubted him, for the idea seemed too grand, too strange. Yet, decades later, satellites confirmed exactly what he had described. The currents that carry energy from space into the aurora now bear his name, a quiet tribute to a man who saw the truth long before instruments could prove it. Birkeland currents are not thin wires but vast sheets of flowing charge, spiraling along the magnetic field lines of the planet like rivers following the contours of a valley. They descend into the polar atmosphere on one side and rise back into space on the other, forming twin pillars of an electric bridge that connects two worlds. When you see the aurora ripple across the heavens, you are watching those currents make themselves known, painting the air with the signature of a physicist who trusted his vision of a universe woven together by invisible threads of electricity. Imagine the magnetic field of the Earth as a set of graceful arches rising from one pole and curving through space to land at the other. Along those arches, charged particles travel with quiet precision, spiraling downward into the atmosphere on one side of the oval and climbing back into the void on the other. The Birkeland currents follow these invisible rails like water flowing through a garden canal, never straying from the path the field has set. Where the current descends, it strikes the thin upper air and makes it glow, creating the arcs and curtains that sweep across the polar night. Where it rises, the light fades and the energy returns to space, ready to circulate once more. This constant flow means that the aurora is not a random splash of color, but a map of moving electricity, each bright line tracing the path of a current that connects the sunlit void of the magnetosphere to the cold air above frozen tundra. The field lines are the architecture, and the light is the evidence that power is flowing through them, silently and without end. During a strong display, the rivers of electricity pouring into the polar sky carry more than 1,000,000 amperes of current. That number is almost impossible to hold in the mind. A household circuit might carry 15 amperes. A bolt of lightning channels 30,000 for an instant. Yet the aurora sustains its million-ampere flow not in a flash, but continuously, minute after minute, as the magnetosphere feeds energy into the night. The current is spread across enormous distances, so it does not concentrate into a single deadly arc. Instead, it fans through the upper atmosphere like a gentle flood, touching countless atoms and coaxing each one to glow. The result is not destruction, but beauty, a paradox of scale where unimaginable power produces only soft, drifting light. Scientists measure these currents with magnetometers on the ground and instruments aboard satellites, tracing the invisible torrents that shape every fold and ripple in the display. To stand beneath a bright aurora and know that 1,000,000 amperes are flowing overhead is to feel the quiet enormity of a planet wired into the electrical heartbeat of its star. High above the poles, where the air is thin enough to carry electricity, a great river of charge flows sideways through the ionosphere. This horizontal stream is called the auroral electrojet, and it races from east to west or west to east, depending on the conditions of the storm. Unlike the vertical Birkeland currents that descend from space, the electrojet moves parallel to the surface of the Earth, connecting regions of inflow to regions of outflow like a bridge between two waterfalls. Its passage disturbs the magnetic field below, causing compass needles to twitch and magnetometers to record sudden shifts in direction. The electrojet can stretch for thousands of kilometers, a silent highway of charge that no eye can see but every sensitive instrument can feel. During powerful storms, its intensity surges and the ground itself responds, picking up faint echoes of the current overhead. The electrojet is part of the aurora's hidden plumbing, the horizontal link that completes the circuit and allows energy to flow continuously from space through the atmosphere and back again without interruption. When the electrojet surges through the ionosphere, its passage sends a ripple downward through the layers of air and into the ground beneath your feet. The magnetic field at the surface shifts, gently but unmistakably, as though the planet itself is responding to the current overhead. Scientists have measured these disturbances for more than a century, recording tiny fluctuations in field strength that correspond precisely to the movements of the aurora above. During strong storms, the changes become large enough to influence compasses and confuse instruments designed for navigation. The effect is a reminder that the aurora is not confined to the sky. Its influence reaches through the atmosphere and into the Earth, linking the highest layers of air to the deepest layers of ground in a single magnetic gesture. The same current that makes the night glow green can make a needle quiver in a quiet laboratory thousands of kilometers to the south. In this way, the electrojet writes its signature not only in light but in magnetism, leaving traces that persist in data long after the color has faded from the heavens. There are nights when the sky appears perfectly dark and still, yet beneath the surface of that calm, invisible currents are flowing. Magnetometers, instruments designed to measure the subtlest shifts in magnetic strength, can sense the passage of auroral electricity, even when the light it produces is too faint for any human eye to catch. These devices sit in quiet stations across the Arctic and Antarctic, recording every tremor in the field with patient precision. When a current strengthens overhead, the magnetometer traces its movement as a wobble in the data, a ghostly signature of energy that the sky has chosen not to reveal in color. This ability to see beyond sight is one of the great gifts of modern science. It tells us that the aurora is always present in some form, a ceaseless whisper of electricity flowing through the polar atmosphere, even on the darkest, clearest nights. The magnetometer listens where the eye cannot, and in its quiet recordings, the invisible life of the sky becomes real and readable. If you could rise above the Earth and look down upon the poles, you would see a ring of light encircling each one. This glowing oval is not drawn by chance. It is the footprint of the Birkeland currents, the place where electricity from space touches the atmosphere and makes it shine. The oval shifts and breathes with the rhythm of the solar wind, expanding when energy surges inward and contracting when the flow subsides. Its shape reveals where the magnetic field lines connect most directly to the turbulent regions of near-Earth space, marking the boundary between sheltered air and the open corridors of the magnetosphere. Every bright arc within the oval traces a channel of descending current, and every dim gap marks a place where the flow is weaker or absent. To see the auroral oval from orbit is to see the planet's electrical architecture laid bare, a living diagram of power drawn in green and violet upon the thin canvas of the upper atmosphere. It is both map and phenomenon, both structure and spectacle, as beautiful as it is precise. The electricity that descends from space does not simply vanish when it reaches the atmosphere. It continues flowing, threading through the ionosphere like water through a network of underground streams until it finds its way back upward along another set of magnetic field lines. The ionosphere, that thin layer of charged gas resting between 80 and several hundred kilometers above the ground, serves as the closing link in the circuit. Without it, the current would have nowhere to go and the aurora would never form. Within this layer, free electrons and ions drift under the influence of electric fields, completing the loop that connects the dayside magnetosphere to the nightside poles. The process is continuous and elegant, a self-sustaining system of flow and return that operates without sound or visible machinery. Every flicker of auroral light is proof that this circuit is alive, that electricity is moving through a pathway older than civilization, connecting the sun to the ground beneath your pillow in one unbroken ring of silent energy. The power carried by the auroral circuit is staggering. During a moderate display, the energy flowing from space into the polar atmosphere can match the output of several large power stations combined. During a strong geomagnetic storm, the figure climbs even higher, reaching levels that dwarf the electrical capacity of entire nations. Yet all of this power is dispersed across a region so vast that it becomes gentle rather than violent, spread thin enough to produce light instead of destruction. The energy arrives as kinetic motion, the speed of charged particles racing along magnetic highways, and it is converted into photons when those particles strike the air. What remains is heat, radio waves, and subtle shifts in the chemistry of the upper atmosphere. The numbers are humbling. Nature runs a power grid above the poles that humanity could never replicate, a system that has operated without failure for billions of years. Every green curtain drifting across the Arctic sky is a reminder that the planet draws more energy from the sun in a single storm than most cities consume in a week. Above the aurora, where the thin air gives way to the near vacuum of space, electric fields build to astonishing strength during geomagnetic storms. The potential difference between regions of the magnetosphere can climb to hundreds of thousands of volts, creating invisible slopes of energy down which charged particles tumble with tremendous speed. These voltages are not concentrated in a single point like a spark, but are spread across vast distances, forming broad electric landscapes that guide the flow of current into the atmosphere. When electrons ride these slopes downward, they arrive at the upper air with enough energy to excite oxygen and nitrogen into brilliant color. The higher the voltage, the deeper and brighter the penetration, and the more vivid the display becomes. It is remarkable to think that the soft green glow drifting above a frozen lake is powered by voltages that would be lethal if concentrated into a single wire. Yet nature distributes them with such care that the result is not danger, but beauty, a spectacle born from forces that operate on a scale far beyond anything found in human engineering. When you watch a bright arc stretch across the sky, clean and sharp against the darkness, you are seeing more than light. You are seeing the edge of an invisible blade of electricity. Auroral arcs form where electric fields concentrate into narrow corridors, accelerating electrons downward with focused intensity. The result is a line of brilliance that can span hundreds of kilometers, yet remain only a few kilometers wide, as precise as a brushstroke drawn by a steady hand. These arcs trace the boundaries where plasma conditions change abruptly, where the magnetosphere organizes its energy into channels of concentrated flow. The sharpness of the arc reveals the sharpness of the field, a place where the transition from calm to energized happens over a remarkably short distance. Scientists study these structures to understand how the magnetosphere sorts and directs its power, because each arc is a window into the invisible forces that shape the display. To the eye, it appears as a ribbon of color. To the physicist, it is a line of data drawn across the sky in living light. Deep within the most sophisticated laboratories on Earth, scientists build enormous machines to accelerate tiny particles to extraordinary speeds. Nature does the same thing above the poles, using electric fields stretched along magnetic lines to fling electrons downward into the atmosphere with energies that rival those of human accelerators. The process is elegant in its simplicity. A voltage difference builds along a field line, and electrons caught in that gradient gain speed as they fall, arriving at the upper atmosphere fast enough to shatter the calm of oxygen and nitrogen atoms and force them to glow. These natural accelerators operate continuously during geomagnetic storms, processing vast quantities of charged particles without any machinery, noise, or visible structure. the sky becomes both the accelerator and the detector, with the aurora serving as the luminous readout of each collision. It is humbling to realize that the physics humanity struggles to reproduce in billion-dollar facilities unfolds effortlessly in the thin air above the Arctic, powered by nothing more than the restless breath of the sun and the patient geometry of Earth's magnetic field. In certain places along the magnetic highways that connect space to the poles, the electric potential does not decline gradually, but plunges suddenly, like a waterfall in an otherwise gentle river. These sharp drops create regions of intense acceleration where electrons gain enormous energy over very short distances. The auroral structures that appear below these drops are among the brightest and most sharply defined in the sky, glowing with a concentrated brilliance that sets them apart from the softer light nearby. Scientists call these features parallel potential drops, and they are one of the keys to understanding why some parts of the aurora blaze while others merely whisper. The drop acts like a gate that opens only for particles with enough momentum to pass through, filtering the flow and concentrating it into a narrow beam that strikes the atmosphere with precision. The resulting light is both beautiful and informative, a bright signature that tells researchers exactly where the invisible architecture of the magnetosphere has folded energy into a point of release. Electricity flows through the Earth and the space around it at every moment, yet almost none of it reveals itself to human eyes. The aurora is the rare exception, a place where planetary-scale currents become visible, where the immense circuitry of the magnetosphere paints itself across the sky in color and motion. Lightning is fleeting. The glow of the ionosphere is too faint, but the aurora persists, sometimes for hours, displaying the paths of currents that connect the sun to the ground in real time. It is a window into a hidden world of electric force that most people never think about, a world where millions of amperes flow in silence above the clouds. To watch the northern lights is to witness the planet's electrical nature made manifest, to see with your own eyes the evidence that Earth is not a passive rock floating in space but an active participant in a cosmic circuit of staggering scale. The aurora turns the invisible into the visible, the abstract into the beautiful, and the silent into something that feels almost alive. The green light that defines the aurora in most people's minds is born from a transition that physics says should almost never happen. Inside an oxygen atom struck by an incoming electron, an outer electron leaps to a higher energy state, and when it falls back, it releases a photon of green light. Under normal laboratory conditions, this transition is so unlikely that it is labeled forbidden, a term that does not mean impossible, but rather extraordinarily rare. In a jar of oxygen at sea level, collisions between atoms happen so frequently that the excited state is interrupted before the photon can escape. The glow is quenched before it begins. But in the upper atmosphere, where the air is thin beyond imagination, the excited atom can wait in silence for nearly a full second, undisturbed, until it finally releases its emerald note. That patience is what makes the green aurora possible. The forbidden becomes permitted only because the sky is quiet enough to allow it. Every green ribbon drifting above the horizon is proof that emptiness itself can be a kind of permission, and that the rarest light sometimes needs only stillness to be born. In the language of quantum physics, the word forbidden carries a meaning softer than it sounds. It does not mean that nature has barred the door. It means that under the crowded, bustling conditions of ordinary matter, the transition happens so rarely that it might as well be invisible. Electrons follow rules about how they can change states, and certain changes violate those rules in a way that makes them extraordinarily slow. In a dense gas, the atom would be jostled by its neighbors long before the transition could complete, and the energy would be lost as heat rather than light. Only in the near vacuum of the upper atmosphere, where atoms drift alone through vast expanses of silence, can these shy transitions find the time they need. The forbidden line of oxygen glows precisely because nothing is there to stop it. The solitude of the thermosphere grants permission that no laboratory ever could. It is a beautiful inversion, one in which emptiness becomes the essential ingredient and the rarest light in the spectrum becomes the most common color in the polar sky. A full second may seem like nothing to a human mind, but in the world of atomic physics, it is an eternity. Most excited states last only billionths of a second before the atom sheds its borrowed energy and returns to rest. Yet the oxygen atoms responsible for the green aurora hold their excitement for close to a second, suspended in a state of quantum patience that would be impossible in denser air. During that long pause, the atom drifts through the thin upper atmosphere, alone and undisturbed, carrying its tiny cargo of energy like a lantern held aloft in a vast, dark room. Only when the moment finally comes does it release the photon, adding one more point of green to the tapestry overhead. This extraordinary delay is what makes the forbidden line possible and what gives the aurora its character. The light we see is not instantaneous. It is the product of waiting, of atoms holding their breath in the silence of near space until the universe allows them to shine. Each green glimmer is a small act of patience made visible across the sky. Not every excited oxygen atom gets to shine. In the denser layers of the atmosphere, where molecules crowd together more closely, collisions happen before the atom has finished waiting. A neighboring molecule bumps into the excited atom and steals its energy, converting what would have been light into a tiny pulse of heat that vanishes without a trace. The photon that might have joined the aurora is never born. This process quietly erases countless potential points of light, thinning the glow from below like a tide retreating from a shore. The suppression explains why the aurora has a lower boundary, a floor below which the air is too thick for forbidden transitions to survive. Above that floor, the atoms find the peace they need. Below it, the crowd consumes their light before it can escape. The balance between emission and suppression is what gives the aurora its vertical structure, painting a band of color at just the right altitude where solitude and energy meet in perfect proportion. Scientists have given this silent theft of light a name. Collisional quenching is the process by which an excited atom loses its energy to a neighbor before it can radiate a photon. The word quenching carries a sense of something being extinguished, and that is precisely what happens. The potential glow is smothered by the presence of too many nearby particles, each one capable of absorbing the energy and turning it into motion rather than light. Quenching is not dramatic. It produces no flash, no sound, no visible event. It is the absence of something that might have been, a photon that was promised but never delivered. Yet this quiet process plays a profound role in shaping the aurora, determining where light can form and where it cannot. The lower edge of every auroral curtain is drawn by quenching, a boundary between two realms, one where atoms are free to glow and another where the crowd denies them that freedom. It is the unseen sculptor of visible beauty, carving the aurora's shape from below. Higher above the green, where the air thins to almost nothing, oxygen atoms can enter an even more patient, excited state. This level holds its energy for more than 2 minutes before releasing a photon of deep red light. 2 minutes in the atomic world is an almost inconceivable span, a silence so long that it would be interrupted 1,000 times over in denser air. Only at the very edge of the atmosphere, where collisions are so rare they might not happen for minutes at a time, can this state survive long enough to complete its slow transition. The red light it produces is softer and more diffuse than the green, spreading across the highest reaches of the display like a crimson veil drawn over the stars. It often crowns the aurora from above, visible only during strong storms when enough energy reaches those extreme altitudes. The red is the aurora's most patient voice, a color that exists only because the sky is quiet enough and empty enough to let an atom hold its breath for longer than almost anything in nature allows. The relationship between patience and altitude is one of the aurora's most elegant truths. The red emission needs more time than the green, and time is a luxury that only the highest, thinnest air can provide. Below 200 kilometers, the atmosphere is still busy enough that collisions quench the red state before it can release its light. Above that height, the density drops until the atom can wait in solitude, undisturbed for the minutes it requires. This is why the red glow appears above the green, layered like a soft halo over the brighter emerald bands. The separation is not arbitrary. It is a direct consequence of quantum mechanics and atmospheric density working together, sorting colors by altitude as surely as gravity sorts water by depth. When you see red light crowning the aurora, you are seeing the signature of extreme emptiness, a realm so thin that even the slowest atomic processes can unfold without interruption. The sky arranges its palette according to the rules of physics, and the result is a vertical rainbow powered not by sunlight, but by the electric breath of the sun. Every color in the aurora carries more information than the eye alone can read. When scientists split the light into its component wavelengths, they find that each emission line is not perfectly sharp, but slightly broadened, spread across a narrow range of frequencies. This broadening reveals the temperature of the gas that produced it, because hotter atoms move faster and shift their light slightly as they do. The faster they move, the wider the line becomes, like a note sung by a chorus of voices slightly out of tune. By measuring this width with precision instruments, researchers can determine how warm the upper atmosphere has become during a storm, reading the temperature of air hundreds of kilometers above the ground without ever leaving the surface. The aurora thus becomes a thermometer written in color, encoding the energy of its environment in the subtle shape of each spectral line. What appears to the naked eye as a single shade of green is, to the spectrometer, a detailed portrait of motion and warmth in the thin air above the poles. The same principle that changes the pitch of a passing siren also changes the color of light from a moving atom. When an oxygen atom glows while drifting toward an observer, its light shifts slightly toward the blue end of the spectrum. When it drifts away, the shift moves toward the red. In the upper atmosphere, atoms move in every direction at once, and the combined effect of all those tiny shifts is a gentle smearing of the emission line, a broadening that scientists call the Doppler effect. The amount of broadening depends on how fast the atoms are moving, which in turn depends on the temperature of the gas. Hotter gas means faster atoms and wider lines. Cooler gas means slower atoms and sharper lines. By studying this effect in auroral light, researchers can peer into the conditions of the upper atmosphere with remarkable precision. Each photon carries the imprint of the atom that released it, encoding speed and direction into its wavelength like a message sealed inside a bottle of green or red light. The broadening of auroral spectral lines does more than reveal temperature. When the atoms producing the light are carried by a wind, the entire emission line shifts in one direction, and the pattern of broadening becomes asymmetric. Scientists can read this asymmetry like handwriting, extracting the speed and direction of winds blowing through the upper atmosphere hundreds of kilometers above the ground. These measurements are invaluable because the thermosphere is too high for weather balloons and too low for most satellites, making it one of the most difficult regions of the atmosphere to study. The aurora provides a natural beacon, a source of light embedded within the very air researchers want to understand. By watching how the spectral lines lean and spread, they can map the invisible rivers of gas that flow above the poles during storms, tracking motion that no other instrument could detect. The aurora is both phenomenon and tool, a light that illuminates not only the sky but the hidden currents of air that move through it in silence. Not all of the aurora's light is meant for human vision. A significant portion of its energy escapes as ultraviolet radiation, wavelengths too short for the rods and cones of our eyes to detect. This invisible glow can be as structured and dynamic as the visible display, forming arcs and curtains that ripple and surge in perfect silence beyond the limits of perception. The ultraviolet emissions come from transitions in both oxygen and nitrogen that release photons with more energy than visible light. Photons that pass through the night unseen by anyone standing below. Only instruments aboard satellites circling above the atmosphere that would otherwise absorb these wavelengths can capture the full picture. When they do, the aurora reveals a hidden layer of complexity, a shadow display that doubles the richness of what the eye perceives. The invisible aurora is a reminder that nature is always larger than our senses allow us to know, and that the sky above the poles is alive with light we will never see without the aid of machines that extend our vision into the unseen. When the sun is above the horizon and the sky is flooded with blue light, the aurora does not stop. Charged particles continue to pour into the poles, striking the upper atmosphere and producing the same emissions as they do at night. The visible light is drowned out by daylight, but the ultraviolet glow persists, detectable by instruments that filter away the sun's contribution and isolate the auroral signal. From orbit, satellites can watch the auroral oval shine at every hour, revealing a display that never truly sleeps. Daytime auroras are just as structured as their nighttime counterparts, with arcs and patches that shift and reform as the solar wind changes. This continuous monitoring has transformed our understanding of space weather, showing that the aurora is a permanent feature of the polar sky, not a nighttime visitor but a constant companion masked by the brightness of day. The satellites reveal a truth that the eye alone could never grasp. The aurora is always there, always glowing, always tracing the invisible architecture of the magnetosphere in light that waits patiently for darkness to be seen. Beyond the red end of the visible spectrum, the aurora radiates in infrared wavelengths that carry information about the heat being deposited in the upper atmosphere. When energetic particles collide with molecules at high altitude, they transfer kinetic energy that warms the surrounding gas. This warmth expresses itself as infrared light, a glow that scientists can detect with specialized instruments. The infrared signature tells researchers how much energy a storm is pouring into the thermosphere and how that energy spreads across the polar regions. During intense events, the heating can be immense, raising temperatures by hundreds of degrees in a layer of air too thin to feel but thick enough to affect the orbits of satellites passing through. The infrared aurora is invisible to the eye and silent to the ear, yet it carries a story of enormous power being absorbed by the atmosphere. Each detection is a data point in the ongoing conversation between the Sun and the Earth, a measure of how much of the star's energy the planet is receiving and how it transforms that energy into motion, chemistry, and warmth. When electrons of extraordinary energy plunge into the polar atmosphere, they do not simply excite atoms into gentle visible light. They strike with such force that the collisions produce X-rays, the same high-energy radiation used in medical imaging. These auroral X-rays are invisible from the ground, absorbed by the layers of air above before they can reach the surface. But from orbit, instruments detect them clearly, mapping regions of the sky where the most energetic particles are raining down. The X-ray aurora reveals the harshest edge of the phenomenon, the places where the magnetosphere channels its most powerful electrons into the atmosphere with violent precision. These events occur during the strongest geomagnetic storms, when the voltages in the magnetosphere climb to their highest levels and the particles they accelerate arrive with enough energy to penetrate deep into the air. The X-ray glow is a reminder that the aurora spans the entire electromagnetic spectrum, from radio waves to X-rays, and that its gentle visible beauty is only one chapter in a much larger and more energetic story. Satellites equipped with X-ray detectors orbit above the atmosphere and look down upon the poles, capturing images of the aurora in a light no human eye has ever seen. The X-ray maps they produce show bright spots and arcs that correspond to the most intense regions of particle bombardment, places where the magnetosphere is pouring its strongest currents into the upper air. These observations are invaluable for understanding the extreme end of the auroral process, the moments when the energy arriving from space reaches levels capable of producing radiation that penetrates far deeper into the atmosphere than visible light alone. Each X-ray image is a portrait of violence rendered in silence, a record of collisions so energetic they would be dangerous to living tissue if they reach the ground. The atmosphere shields us from this harsh light, absorbing it in layers of air that grow denser with every kilometer of descent. From orbit, however, the full picture emerges, and the aurora reveals itself not just as a gentle shimmer but as a phenomenon of formidable power, radiant across wavelengths that span the entire spectrum of light. The brightness and distribution of auroral light encode information about the air through which it passes. By measuring how intense the glow is at different altitudes, scientists can calculate the density of the atmosphere at each height, determining how many atoms and molecules are present in each thin layer. This technique turns the aurora into a natural probe, a source of light embedded within the very medium it illuminates. Denser air produces brighter emissions because there are more atoms available to collide with incoming particles. Thinner air produces fainter light because encounters are fewer. The gradient of brightness from the base of the aurora to its upper reaches draws a vertical profile of atmospheric density that can be read like a chart. This remote sensing capability is especially valuable because the upper atmosphere is notoriously difficult to sample directly. Rockets pass through it in seconds, and satellites orbit above it. The aurora alone provides a continuous, real-time portrait of conditions in the region where space and air meet, glowing with data that scientists can harvest from the safety of the ground. Most of the oxygen that glows in the aurora exists as individual atoms, broken apart by the energy of incoming particles. But deeper in the atmosphere, where the air is denser, oxygen molecules survive intact, and their emissions produce a different set of spectral lines. These faint glows are difficult to detect because they are often overwhelmed by the brighter atomic emissions above, yet they carry unique information about conditions in the lower reaches of the auroral display. When scientists identify molecular oxygen lines in the spectrum, they can determine how deeply the incoming electrons are penetrating, because molecular oxygen is found primarily at altitudes where the air is thick enough to support molecules rather than lone atoms. The detection of these faint emissions is like hearing a whisper beneath a song, a subtle voice that speaks of depth and density in the atmospheric layers below the main curtains of light. Each molecular signature adds another dimension to the story the aurora tells, revealing how the energy from space distributes itself through the many-layered air above the world. By comparing the brightness of the red and green emissions in the aurora, scientists can deduce the energy of the particles creating the display. Higher energy electrons penetrate deeper into the atmosphere, where they excite oxygen at altitudes favorable for green light. Lower energy electrons deposit their energy higher up, where the long-lived red state dominates. The ratio between the two colors thus becomes a measure of how energetic the incoming stream is, a natural gauge that updates in real time as conditions change. When the green dominates, the storm is driving particles deep. When the red grows stronger, the energy is being deposited at greater heights. This spectral arithmetic allows researchers to monitor the magnetosphere's behavior by simply watching the sky, reading the balance of colors as one might read the expression on a face. The aurora is generous with its information, encoding the physics of its birth in the very hues it wears. Each shift in the red to green ratio is a message about conditions far above, translated into color for those who know how to listen. Every shade in the aurora is a sentence written in the language of physics. Green speaks of oxygen atoms at 100 kilometers, excited by electrons of moderate energy in air thin enough to permit the forbidden transition. Red whispers of extreme altitude and extraordinary patience, where atoms hold their energy for minutes in near-perfect solitude. Blue and purple announce the presence of nitrogen, its molecular bands vibrating with the speed of collisions in denser air. Ultraviolet and infrared add chapters that the eye cannot read but instruments decode with precision. Together, these colors form a document more detailed than any written report, a real-time account of temperature, density, altitude, particle energy, and chemical composition in the upper atmosphere. Scientists have learned to read this document with increasing fluency, extracting information that was once locked away in the sky's silence. The aurora is both canvas and code, both spectacle and signal. Its beauty is not separate from its meaning. The two are one and the same, each photon carrying wonder and data in equal measure across the dark. What hangs above the poles is not merely a spectacle for the eye, but a living instrument for the mind. The aurora diagnoses the state of the upper atmosphere in real time, reporting on temperature, composition, density, wind speed, and the energy of incoming particles through the precise wavelengths and intensities of the light it emits. No other natural phenomenon provides so much information so continuously and so visibly. Scientists read the aurora the way a physician reads vital signs, interpreting each color, each flicker, each shift in brightness as a clue to the conditions of the invisible environment above. The diagnostic power of the aurora extends beyond the atmosphere itself. By tracing the patterns of light, researchers can infer the state of the magnetosphere, the behavior of the solar wind, and the configuration of magnetic fields millions of kilometers away. The aurora is a translator, converting the silent dynamics of space into a form that can be seen, measured, and understood. It is nature's own monitoring system, and its readout is written in the most beautiful language imaginable. Deep beneath the surface of the Greenland ice sheet, layers of compressed snow hold memories of skies that glowed centuries ago. When powerful solar storms struck the Earth in ages past, they altered the chemistry of the upper atmosphere, producing compounds that drifted downward through the air and settled into the falling snow. Over time, that snow was buried and compressed into ice, locking those chemical traces into a frozen archive that scientists can now drill out and read. Elevated levels of certain substances in the ice correspond to periods of intense solar activity, moments when the aurora may have blazed far beyond its usual boundaries. Each core is a timeline stretching back thousands of years, a record of the sun's behavior written not in ink, but in molecules preserved by cold. By studying these layers, researchers can reconstruct the history of space weather, identifying storms that occurred long before any instrument existed to measure them. The ice remembers what the sky has forgotten, holding in its frozen depths the faint chemical echoes of auroras that lit the ancient world. Among the chemical fingerprints preserved in ice cores, nitrate holds a special place. When intense auroral activity floods the upper atmosphere with energy, nitrogen and oxygen combine to form nitric oxide, which eventually transforms into nitrate as it descends through the air. This nitrate settles into snow and is preserved in the ice below, creating spikes in concentration that can be matched to known periods of extreme solar activity. Scientists have found that some of these spikes align with historical records of brilliant auroras seen far from the poles, confirming the connection between the chemistry in the ice and the light in the sky. The nitrate signal is not always clean. Other processes can also produce nitrate, and teasing apart the sources requires careful analysis. Yet, when the evidence converges, it tells a remarkable story of how the breath of the sun can leave a chemical trace that persists for millennia, frozen into the Earth itself. Each spike in the data is a fossilized aurora, a memory of light encoded in the quiet chemistry of ancient snow. Trees grow a new ring each year, and within those rings, the ratio of carbon-14 to ordinary carbon reflects the intensity of cosmic rays reaching the Earth's atmosphere. When the sun is active and its magnetic field is strong, it deflects many cosmic rays, reducing carbon-14 production. When a sudden extreme solar event overwhelms even this shielding, the burst of energetic particles can actually increase carbon-14 production dramatically, leaving a sharp spike in the tree ring that corresponds to that year. Scientists have discovered these spikes in trees from around the world, all pointing to the same moments in history when the sun unleashed extraordinary energy. The trees knew nothing of auroras, yet they recorded the same solar outbursts that would have lit the sky from pole to equator. Each ring is a chapter in a long, quiet diary kept by organisms that stood rooted in the soil while the heavens blazed above them. The connection between a tree's chemistry and a solar storm is one of science's most beautiful threads, linking the smallest organic detail to the largest cosmic events. In the record of ancient tree rings, certain carbon-14 spikes stand out for their extraordinary size. These rare and dramatic increases are now called Miyake events, named after the Japanese researcher who first identified them. They represent moments when the sun, or possibly another cosmic source, released a surge of energy so intense that it left a permanent mark in the chemistry of every living tree on Earth. The events are separated by centuries or millennia, and their exact cause is still debated, though the leading explanation involves extreme solar particle storms far more powerful than anything recorded in modern history. If such events produced auroras, the displays would have been staggering, visible around the entire globe and lasting for days. The Miyake events remind us that the sun is capable of outbursts beyond anything we have witnessed in the age of instruments. They are warnings written in wood, preserved by the quiet patience of trees that outlasted the storms and carried the memory forward in their rings for scientists to discover thousands of years later. In the year 774 of the Common Era, something extraordinary happened in the sky. Tree rings from that period show one of the largest carbon-14 spikes ever recorded, indicating a massive influx of energetic particles into Earth's atmosphere. If this event was solar in origin, as many scientists believe, the geomagnetic storm would have been ferocious, flooding the magnetosphere with energy and driving the aurora far beyond the poles. Historical records from that era are sparse, but scattered accounts from China, Europe, and the Middle East describe unusual lights in the sky that align with the timing of the spike. The aurora that night, or series of nights, may have painted the heavens from the Arctic to the tropics, covering the world in a spectacle of color that no one alive could explain. The event left its signature in tree rings across every continent, a silent witness to a cosmic upheaval that touched the entire planet. It stands as a reminder that the sun has spoken before in voices louder than any modern storm, and that the aurora was once, for a brief and brilliant moment, a truly global phenomenon. Across centuries of meticulous record-keeping, Chinese astronomers and court historians documented strange lights in the night sky with remarkable detail. Their accounts describe glowing red and white apparitions that lasted for multiple nights, sometimes covering large portions of the heavens. These descriptions are consistent with powerful geomagnetic storms that would have driven the auroral oval southward to latitudes visible from China. For a civilization rooted in careful observation of celestial omens, such events were significant enough to warrant official notation, preserving details that modern scientists now use to reconstruct the history of space weather. The Chinese records are among the oldest and most extensive descriptions of auroras outside the Arctic, providing a timeline of solar activity stretching back more than 2,000 years. When matched with evidence from ice cores and tree rings, these written accounts confirm that the aurora has occasionally reached into temperate and even subtropical skies. They are a gift across time, bridging the ancient practice of skywatching with the modern science of magnetospheric physics through the simple act of writing down what was seen. The magnetic poles of the Earth do not sit in one place forever. Over spans of thousands of years, they wander, weaken, and sometimes reverse entirely, trading north for south in a slow upheaval of the planet's magnetic architecture. During such transitions, the magnetic field grows significantly weaker and its structure becomes more complex, with multiple poles and tangled field lines replacing the neat dipole that normally shields the planet. In such a weakened state, the aurora would no longer be confined to narrow ovals around two poles. Instead, it could bloom across much wider regions of the sky, appearing at latitudes where it is never seen today. The auroral display during a reversal might look nothing like the tidy arcs and curtains of the modern era. It could be scattered, unpredictable, and visible from places that have never known its light. The possibility is a reminder that the aurora's geography is not fixed. It is shaped by a magnetic field that has its own slow, ancient rhythm, one that redraws the map of light across the sky over timescales far longer than any human life. If the Earth's magnetic shield were to thin, the consequences for the aurora would be immediate and visible. A weaker field cannot channel incoming particles as effectively, and the regions where those particles reach the atmosphere would broaden. Auroras that currently appear only near the poles would creep toward the equator, becoming visible from cities and landscapes that have never experienced them. The light would not be brighter, but its reach would be wider, spreading like watercolor across a larger canvas. Scientists studying the gradual weakening of the field in certain regions, such as the South Atlantic anomaly, have already observed faint effects that suggest this process is underway in a localized fashion. A global weakening of the kind that precedes a pole reversal would amplify these effects enormously. People living in temperate climates might look up one winter night and see faint green veils where only stars had been before. The aurora would become a visitor in unfamiliar skies, a quiet signal that the planet's invisible armor is shifting beneath the silence of the night. A geomagnetic reversal is not a sudden flip like a switch being thrown. It is a slow, meandering process that unfolds over thousands of years, with the magnetic field weakening, fragmenting, and gradually reorganizing itself into a new orientation. During this transition, the field can develop multiple poles, creating a magnetic landscape far more complex than the simple dipole we know today. The evidence for these reversals comes from rocks, particularly volcanic basalts that lock in the direction of the magnetic field at the moment they cool and solidify. Layer by layer, these rocks record the history of the field, showing periods of stability punctuated by episodes of confusion and change. The most recent full reversal happened roughly 780,000 years ago, and the next could begin at any time on a geological scale. During the long twilight of a reversal, the aurora would be in flux, its patterns shifting and wandering as the field reconfigures itself. It would be a sky unlike any we have known, painted by a planet in the act of rewriting its magnetic identity. When the magnetic field loses its clean dipole symmetry, the paths that charged particles follow into the atmosphere become tangled and unpredictable. Instead of two neat ovals circling two poles, the aurora might appear in scattered patches, wandering arcs, or multiple rings corresponding to the many magnetic centers that emerge during a transition. The familiar curtains and ribbons could give way to shapes no one alive has ever seen, structures molded by a field that has no single axis and no simple geometry. Scientists can model these scenarios using computer simulations, and the results are striking. The aurora during a transitional period would be a thing of wild, fragmented beauty, appearing in unexpected places and shifting with the restless motion of a field searching for its new equilibrium. The display would be a living portrait of magnetic chaos, a sky in which the rules that normally organize the light have been temporarily suspended. For those who might witness such an era, the northern lights would become something entirely new, a spectacle without borders or precedent. If the magnetic field were to fragment into several poles during a reversal, each pole would attract its own share of charged particles from space. The result would be multiple auroral ovals scattered across the globe, each one tracing the footprint of a different magnetic center. Imagine looking up from a desert and seeing a ring of light that belongs not to the North or South Pole, but to a temporary magnetic concentration beneath your feet. The possibility is extraordinary, a planet wearing many crowns of light instead of just two. While no human has witnessed such a configuration, the physics is sound. Wherever magnetic field lines converge and descend into the atmosphere, charged particles will follow and the air will glow. During a transitional period with multiple poles, the aurora would lose its polar identity entirely, becoming a global phenomenon distributed by the complex geometry of a field in flux. The idea stretches the imagination, but it also deepens appreciation for the aurora as we know it today, a phenomenon shaped by the stable two-poled field that humanity has always known. Mars lost its global magnetic field billions of years ago, yet the red planet has not entirely forgotten the light. Scattered across the Martian surface, patches of ancient magnetism remain locked within the crust, preserved like fossils of a once active core. When the solar wind sweeps across Mars, charged particles follow these residual field lines down into the thin atmosphere, producing faint, localized auroras that flicker above the magnetic remnants below. Spacecraft orbiting Mars have detected these glows in ultraviolet wavelengths, mapping them against the known distribution of crustal fields. The auroras do not form ovals or arcs. They appear as irregular patches, each one tethered to the rock beneath it like a ghost light hovering over a buried magnet. The discovery has given scientists a unique window into what happens when a planet's magnetic defense crumbles. Mars stands as a cautionary tale, a world that once may have glowed with global auroras but now shows only the faint, scattered remnants of that former brilliance, dimming slowly as the crustal fields weaken under the relentless wind of the sun. By observing how the solar wind interacts with the remnant magnetic patches on Mars, scientists can build models of what Earth's magnetosphere might have looked like during its own periods of weakness and transition. Mars serves as a natural laboratory for studying a planet with a fragmented field, providing data that no simulation alone could produce. The localized auroras on Mars reveal how charged particles behave when there is no global magnetic shield to organize them, scattering across the surface wherever a pocket of magnetism offers a foothold. These observations help researchers predict what might happen to Earth's aurora if the field weakens significantly during a future pole reversal. The comparison between the two worlds is both illuminating and humbling. Earth still wears its magnetic armor intact, channeling the sun's energy into two glowing ovals that circle the poles with elegant symmetry. Mars shows what lies on the other side of that armor, a future that the Earth may one day approach when the lights grow scattered and the shield grows thin. The magnetic field that shapes the aurora is not static. It pulses with a slow rhythm that plays out over hundreds and thousands of years, strengthening in some eras and weakening in others. Measurements taken since the 19th century show that the field has been gradually declining in overall strength, a trend that has led some to wonder whether a reversal might eventually follow. The changes are subtle enough that no one would notice within a single lifetime. Yet over centuries, the cumulative shift can alter where the aurora appears and how brightly it shines. A stronger field funnels particles more tightly, producing sharper, more concentrated auroras closer to the poles. A weaker field allows the oval to widen and the light to spread. The slow heartbeat of the field is one of the Earth's oldest rhythms, driven by the churning convection of molten iron deep in the planet's core. Every aurora we see tonight is shaped by the current state of that ancient pulse, and the auroras of the future will be shaped by wherever that pulse carries the field next. As the magnetic field loses strength, the invisible funnel that channels charged particles toward the poles grows wider. The aurora, which now clusters near the Arctic and Antarctic, would begin to appear at lower and lower latitudes, creeping southward with each passing century until it becomes visible from places that have never known its light. The change would be imperceptible within a human generation, a slow migration of green and violet toward the equator that no single observer would notice. Yet, over the span of millennia, the shift would transform the experience of the night sky for billions of people. Cities that have only ever seen the aurora in photographs would begin to witness it firsthand, faintly at first, then with increasing frequency and strength. The phenomenon would no longer belong exclusively to the far north and south. It would become a feature of temperate and even subtropical skies, a new companion to the constellations. The possibility is a quiet reminder that the Earth is always changing, and that the sky we know tonight is not the sky that will always be. When astronauts look down upon the Earth from the windows of the International Space Station, the aurora reveals its truest shape. It is not a curtain or an arc, but a ring, a luminous oval that encircles each magnetic pole like a crown placed upon the planet by the solar wind. The ring stretches for thousands of kilometers, its edges bright with green and violet light, its interior dark where the magnetic field lines arc upward into space. From this vantage, the scale of the display becomes overwhelming. What appears from the ground as a single ribbon is revealed to be one small segment of a structure that spans continents and oceans. The ring breathes with the rhythm of the solar wind, swelling when energy increases and shrinking when the wind subsides. Time-lapse footage from orbit shows this breathing in accelerated motion, the oval expanding and contracting like a living organism responding to invisible forces. To see the aurora from above is to understand that the lights are not a local event, but a planetary one, a halo that belongs to the Earth itself. The auroral oval is never still. It responds to every shift in the solar wind with a corresponding change in size, brightness, and shape. When a gust of charged plasma arrives from the sun, the oval swells outward, pushing its boundary toward lower latitudes and engulfing regions that normally lie outside its reach. When the wind slackens, the oval contracts again, drawing back toward the pole like a tide retreating from the shore. This breathing pattern can unfold over hours or days, and its rhythm is dictated entirely by conditions in space. Scientists monitor the oval using satellite imagery, watching it pulse with every substorm and surge with every coronal mass ejection. The expansion is not uniform. Some sectors grow faster than others depending on the direction and strength of the incoming magnetic field. The result is an oval that stretches and tilts, finding new shapes as it adapts to the ever-changing pressure of the solar wind. It is a living boundary, drawn and redrawn by forces that reach across millions of kilometers of empty space. Among the many shapes the aurora can take, spirals are among the most striking and least expected. Satellite images occasionally reveal vast swirling patterns in the auroral oval, where bright arcs curl inward like the arms of a galaxy or the vortex of a storm. These spirals form when large-scale instabilities in the magnetosphere create rotational flows of plasma that map themselves onto the upper atmosphere. The light follows the motion, tracing the unseen turbulence above in a shape that feels both alien and familiar. Spirals appear most often during the expansion phase of substorms, when energy is being released rapidly and the magnetic field is reorganizing itself in complex ways. From the ground, only fragments of the spiral might be visible, appearing as unusually curved arcs that bend in unexpected directions. But from above, the full pattern emerges, revealing a level of order within the chaos that is both beautiful and deeply informative. Each spiral is a snapshot of the magnetosphere in motion, a frozen moment of cosmic turbulence written in light upon the polar sky. When conditions are right, the aurora in the north and the aurora in the south mirror each other with striking fidelity. Satellite imagery captured simultaneously over both poles shows ovals of similar size, brightness, and structure, as though the planet were wearing matching rings of light. This symmetry arises because the same magnetic field lines connect both hemispheres, threading energy from space into matching footprints at each pole. The particles that create one display are often linked by field lines to those creating the other, so changes in one oval tend to echo in its twin. The symmetry is most apparent when the solar wind arrives with its magnetic field oriented in a way that treats both hemispheres equally. It is a reminder that the aurora is not a local phenomenon but a global one, a pair of luminous mirrors reflecting the same cosmic energy from opposite ends of the Earth. To see both ovals simultaneously is to see the planet as a unified magnetic system, connected from pole to pole by invisible threads that carry light across the full diameter of the world. Perfect symmetry is an ideal that nature approaches but rarely achieves. The northern and southern auroras often differ in subtle ways, influenced by small asymmetries in the magnetic field, the tilt of the Earth's axis, and the direction of the solar wind's embedded magnetic field. One oval may be slightly larger, brighter, or shifted relative to its twin, creating a mismatch that reveals the complexity of the system. Seasonal differences play a role as well. When one hemisphere is tilted toward the sun and the other away, the conditions for auroral formation differ and the displays diverge. Scientists study these asymmetries carefully because they encode information about how the magnetosphere distributes energy between the two poles. Each difference is a clue to the three-dimensional structure of the magnetic field and the currents that flow through it. The departures from symmetry are not flaws. They are features, revealing the subtle ways in which a planet's relationship with its star is never quite the same from one pole to the other. During the most intense geomagnetic storms, the auroral oval does not merely brighten, it fills. The ring of light that normally encircles the pole expands until it covers the entire polar cap, wrapping the top of the world in a continuous blanket of luminous color. From space, the effect is breathtaking. The normally dark interior of the oval glows with diffuse light, and the boundaries blur as energy floods every corner of the polar ionosphere. On the ground, observers beneath the cap see light in every direction, above, behind, and to every side, as though the sky itself has become a single radiant dome. These events are rare and require the magnetosphere to be pushed to its limits by an overwhelming surge of solar energy. When they occur, they represent the aurora at its most extreme, a phenomenon that has abandoned its usual restraint and claimed the entire polar sky as its stage. The experience of standing beneath a fully wrapped aurora is unlike any other, a complete immersion in light that makes the horizon itself seem to glow. When a substorm erupts, the change is visible from orbit in an instant. The midnight sector of the auroral oval, the region facing directly away from the sun, suddenly flares to life with a brightness that outshines everything around it. The surge appears as a bloom of intense light that expands outward from a single point, engulfing the surrounding arcs and filling the midnight sky with radiance. Satellite cameras capture this brightening as a dramatic pulse in their time-lapse recordings, a heartbeat of energy released from the magnetic tail. The expansion lasts only minutes, but during that time, the midnight sector becomes the most luminous region on the entire planet's night side. Scientists study these brightenings to understand how and where magnetic reconnection triggers the release of stored energy, because the location and timing of the surge reveal the dynamics of the invisible magnetosphere above. From the ground, the same event is experienced as a sudden eruption of motion and color, curtains leaping and surging as the sky comes alive. From space, it is a flash of planetary significance, a signal that the Earth has exhaled. The light of the aurora is measured in a unit called the Rayleigh, named after the physicist Lord Rayleigh, who studied the faint glow of the night sky. One Rayleigh corresponds to an extremely small amount of light, a quantity chosen specifically to describe the dim emissions of the upper atmosphere. The unit allows scientists to compare auroral brightness across different events, wavelengths, and locations with precision. A faint aurora might glow at a few hundred Rayleighs, visible only to sensitive cameras. A moderate display might reach several thousand, visible to the adapted human eye. A strong storm can push the brightness above 10,000 Rayleighs, producing light vivid enough to illuminate the ground below. By expressing the aurora's brightness in this standardized way, researchers can track how the display evolves over time and compare measurements taken from different instruments and platforms. The Rayleigh gives the aurora a number to accompany its color, a way of quantifying the beauty of the sky in terms that allow the data to travel from one laboratory to another across the world. When the magnetosphere opens wide and energy pours into the polar atmosphere without restraint, the aurora can reach extraordinary brightness. At 10,000 Rayleighs or more, The light is no longer a subtle presence. It is a force that reshapes the night. Snow-covered fields glow green, shadows appear beneath trees and buildings as if an invisible moon has risen, and the sky becomes a churning sea of radiance that seems to press down upon the landscape. These intense displays occur during the largest geomagnetic storms, when millions of amperes of current flow into the ionosphere and the electric potential above the poles climbs into the hundreds of thousands of volts. The energy deposited in the atmosphere during such events can heat the upper air by thousands of degrees, expanding it outward and altering satellite orbits. On the ground, the experience is overwhelming. The brightness transforms the aurora from a distant spectacle into an intimate presence, a light so vivid it seems alive, so close it seems to breathe. These are the nights that etch themselves into memory and into the scientific record in equal measure. From the windows of the International Space Station, astronauts witness a perspective of the aurora that no ground observer will ever share. The curtains of light do not hang overhead but stretch along the curved edge of the planet, draped like luminous fabric over the limb of the Earth. The green and violet bands glow against the blackness of space, their lower edges touching the atmosphere and their upper tendrils reaching toward the stars. The sight blurs the boundary between planet and cosmos, between the familiar and the unknown. Astronauts have described the experience as one of the most moving moments of spaceflight, a reminder that the Earth is alive with energy that extends far beyond the surface. Some have watched the station pass directly through the upper fringes of the display, surrounded by a faint glow that seemed to enter the cabin itself. The aurora from above is not just beautiful, it is humbling, a revelation of the planet's dynamic relationship with the sun, visible in a way that makes every photograph and every description feel like a pale shadow of the real thing. Astronauts aboard the station carry cameras with long exposure settings, and they use them often to capture the aurora as it passes beneath the orbit. These images have become some of the most iconic photographs of Earth from space, showing the glowing oval stretching across entire continents, its edges sharp and bright, its interior dark or filled with diffuse light depending on the storm. The photographs provide both beauty and data, revealing structures in the aurora that ground-based observers cannot see. From above, the full extent of the oval is visible at a glance, along with the fine details of individual arcs and patches that would be foreshortened or hidden from below. The station's orbit carries it over the auroral zone several times each day, providing a regular opportunity to document the display under varying conditions. Each photograph adds to a growing archive that scientists use to study how the aurora responds to solar activity over time. The images also serve another purpose. They remind the world that the northern and southern lights are not separate phenomena, but twin expressions of a single planetary process, visible in full only from the silence of orbit. The aurora that appears smooth and flowing from below often reveals a hidden complexity when seen from orbit. Satellite images and photographs from the space station show that many arcs are composed of fine filaments, narrow threads of brightness running parallel to each other within the broader band. These filaments can be only a few kilometers wide, far too thin to resolve from the ground, yet they carry important information about the structure of the electric fields and currents that create them. Each filament corresponds to a channel of concentrated energy, a narrow corridor where the electric field has focused the incoming particles into a tight beam. The finer the filaments, the more organized the energy flow and the more information scientists can extract about conditions in the magnetosphere above. The discovery of these structures changed the way researchers think about the aurora, revealing that even the simplest-looking arc is in fact a bundle of many individual threads, each one a separate pathway of electricity flowing from space into the air. The smooth beauty seen from below is, from above, a tapestry woven from countless individual strands. The narrowest auroral arcs are so thin that they would fit comfortably within the boundaries of a small town. These slender ribbons of light stretch for hundreds or thousands of kilometers along the east-west direction, but measure only a few kilometers from edge to edge. Their thinness is a testament to the precision with which the magnetosphere can focus its energy, channeling particles into beams so narrow that the resulting light forms a line rather than a band. These arcs are often the brightest features in the display because the energy is concentrated rather than spread. They glow with an intensity that can outshine the broader, more diffuse structures around them, and their sharp edges reveal the presence of steep gradients in the electric field. From the ground, a narrow arc appears as a brilliant line drawn across the sky, steady and defined, cutting through the softer glow around it like a thread of pure light. From space, its dimensions become clear, and the precision of the forces that created it becomes visible in the sharpest possible terms. When scientists compress hours of satellite imagery into seconds of time-lapse video, the aurora reveals patterns of motion that are invisible in real time. Waves of brightness ripple across the auroral oval, traveling from one side to the other like swells on an ocean of light. These waves correspond to disturbances in the magnetosphere that propagate along the field lines and through the plasma, modulating the flow of particles into the atmosphere as they pass. The time-lapse reveals a display that is not chaotic but rhythmic, governed by waves and oscillations that repeat with regularity and travel with measurable speed. Some waves span thousands of kilometers, affecting the aurora across an entire hemisphere in a single sweep. Others are smaller and more localized, creating ripples within ripples that add complexity to the overall motion. The effect is mesmerizing, a view of the planet's electrical heartbeat rendered visible in compressed time. The aurora, which from the ground seems to move slowly and unpredictably, is revealed from above to be a system governed by wave physics, as orderly in its way as the tides of the ocean. On active nights, the aurora can stretch from one edge of the visible horizon to the other, forming a continuous band of light that refuses to break. These uninterrupted bands can span entire continents, arcing across the sky in a single, unbroken line that traces the curve of the auroral oval. From space, they appear as luminous threads woven into the fabric of the night, connecting regions separated by thousands of kilometers of ocean and ice. The continuity of these bands reveals the coherence of the current systems that create them. A single sheet of Birkeland current can descend into the atmosphere across an enormous area, producing a band of light that is uniform not because of coincidence but because the energy feeding it flows as one. To stand beneath such a band and trace it from horizon to horizon is to feel the scale of the phenomenon, the awareness that the same light touching the sky above your head extends far beyond anything you can see, joining your night to the nights of strangers thousands of kilometers away beneath the same luminous thread. In the invisible ocean of plasma that fills near-Earth space, waves of energy ripple through the charged particles like wind through a field of grass. These plasma waves can travel vast distances along magnetic field lines, carrying oscillations that modulate the flow of electrons streaming toward the atmosphere. When a wave crest passes, more electrons are pushed downward and the aurora brightens. When a trough follows, the flow diminishes and the light dims. The result is a rhythmic pulsation in the aurora's brightness that reflects the wave patterns in the space above. Scientists detect these modulations with sensitive ground-based cameras and correlate them with satellite measurements of wave activity in the magnetosphere. The connection reveals that the aurora is not simply a product of steady currents, but a dynamic response to the turbulent wave environment of space. Each flicker and pulse in the display is tied to an invisible oscillation overhead, a tremor in the plasma that translates itself into the rhythm of light. The aurora breathes because the space around the Earth breathes, and the two are joined by waves that travel the magnetic threads between them. Among the many types of waves that travel through plasma, Alfvén waves hold a special place in auroral science. Named after the Swedish physicist Hannes Alfvén, these waves propagate along magnetic field lines like vibrations along a plucked string, carrying energy from the distant magnetosphere directly into the polar ionosphere. When an Alfvén wave reaches the upper atmosphere, it deposits its energy into the gas below, accelerating electrons and igniting patches of auroral light. The waves can be generated by disturbances in the solar wind, by instabilities in the magnetosphere, or by the reconnection events that trigger substorms. Their ability to transport energy over enormous distances without significant loss makes them one of the primary mechanisms by which the magnetosphere powers the aurora. Scientists have measured these waves with satellite instruments, tracing their paths from the magnetic tail down into the polar sky. Each wave is a messenger, carrying the story of distant turbulence along the magnetic strings of the Earth and translating it into the gentle, visible language of light above the frozen world below. When waves in the plasma encounter the charged particles spiraling along magnetic field lines, the two can exchange energy in subtle and complex ways. Some particles gain speed and others lose it, depending on whether the wave and the particle are moving in harmony or opposition. These interactions can cause electrons to scatter into the atmosphere in pulses, creating auroral pulsations that repeat with the rhythm of the underlying wave. The process is called wave-particle interaction, and it is one of the fundamental mechanisms of plasma physics. In the context of the aurora, it explains why some patches of light blink in steady patterns while others remain constant. The pulsation is not random. It is the product of a resonance between the wave and the particle population, a coupling that converts invisible oscillations into visible rhythm. Scientists study these pulsations to understand how energy is transferred from the vast reservoir of the magnetosphere into the thin layer of air where light is born. Each blink is a signature of resonance, a moment where wave and particle meet and agree to create a heartbeat of color. Certain auroral arcs do not simply glow steadily or flicker randomly. They vibrate at specific frequencies, oscillating in brightness or position with a regularity that reveals the influence of plasma resonance. These frequencies correspond to natural modes of vibration in the magnetospheric plasma, the same way a drumhead vibrates at specific pitches determined by its size and tension. When the aurora oscillates at one of these natural frequencies, it becomes a visible indicator of the invisible standing waves that fill near-Earth space. Scientists measure these oscillations with high-speed cameras and correlate them with satellite data to identify which plasma modes are active during a given event. The result is a picture of the magnetosphere as a resonant cavity, a vast magnetic chamber in which energy bounces back and forth in patterns as regular as the tones of a musical instrument. The aurora, in this view, is the instrument's visible output, a display of the vibrations that fill the space around the Earth, translated from plasma physics into living, breathing light. At its most rapid, the aurora flickers so quickly that the human eye cannot follow. High-speed cameras recording at hundreds of frames per second reveal that some patches of light blink on and off dozens of times in a single second, creating a strobe effect that is invisible to unaided vision. This rapid flickering is caused by waves in the magnetosphere that modulate the electron flow at frequencies far beyond the threshold of human perception. Each flash corresponds to a pulse of particles striking the atmosphere, followed by a brief pause as the wave passes through its trough. The effect is astonishing when viewed in slow motion. The sky seems to shudder with rapid, rhythmic light, as if the atmosphere itself were vibrating like a membrane struck by an unseen hand. These rapid pulsations carry information about the frequencies of the waves driving them, providing scientists with a tool for studying magnetospheric dynamics through the aurora's visible response. What seems calm and steady to the naked eye is, in the language of high-speed imaging, a world of furious, invisible rhythm. Standing beneath an aurora that appears calm and smoothly flowing, you might never suspect that the light is racing through dozens of cycles each second. The human eye, evolved to track the motion of predators and prey across a sunlit landscape, is not built to resolve rapid fluctuations in dim light. Our visual system blends the rapid flashes together into a continuous glow, smoothing the staccato into a legato that feels gentle and unbroken. This perceptual blending is a kindness of biology, turning what would otherwise be a disorienting strobe into a serene display. Yet beneath that serenity, the truth is one of extraordinary speed. The electrons arriving from space are modulated by waves that cycle dozens of times per second, and each cycle leaves a trace of brightness in the upper air that is too brief for consciousness to catch. Technology reveals what the senses cannot. High-speed cameras and photometers peel back the illusion of smoothness and show the rapid heartbeat within. The calm aurora is a beautiful deception, and its hidden rhythm is one of its most remarkable secrets. Scattered across the polar regions, radar installations send radio beams upward into the ionosphere and listen for the echoes that return. During auroral activity, the plasma in the ionosphere develops irregularities, small-scale structures, and density variations that scatter the radar signal in distinctive patterns. By analyzing these echoes, scientists can map the motion of the plasma in real time, tracking flows that correspond to the electric currents and fields creating the aurora above. The radar sees what the eye cannot, revealing a turbulent landscape of moving charge that underlies the visible display. These measurements are crucial for understanding how energy from the magnetosphere couples into the ionosphere and how the resulting currents shape the patterns of light. The radar also provides information about wind speeds and temperatures in the upper atmosphere, complementing the optical data from cameras and spectrometers. Together, these instruments create a multidimensional portrait of the auroral environment, where every flicker of light is accompanied by a corresponding tremor in the plasma that the radar faithfully records from its quiet station below. When the aurora blazes at its brightest, the ionosphere beneath it becomes a sea of turbulence. The powerful electric currents flowing through the plasma heat and stir the charged gases, creating waves, eddies, and irregularities that ripple through the ionospheric layers. This turbulence is invisible from the ground, but its effects are felt across modern technology. Radio waves passing through the disturbed ionosphere are scattered and refracted, losing their coherence and degrading the signals they carry. The turbulence is strongest directly beneath the brightest auroral arcs, where the current density is highest and the energy input is most intense. Scientists study these disturbances to understand how energy is dissipated in the upper atmosphere and how the resulting chaos affects communication and navigation systems. The turbulence is a hidden consequence of the aurora's beauty, a reminder that the same forces that paint the sky with color also churn the invisible medium through which our signals travel. The bright curtains overhead cast shadows in the electromagnetic world below, disrupting the quiet pathways of radio and satellite communication. Radio waves traveling through a calm ionosphere follow predictable paths, bending and reflecting in ways that engineers have learned to manage over decades. But when auroral turbulence stirs the plasma into chaos, those paths become unreliable. The irregularities in electron density scatter the radio signals, deflecting them from their intended course and causing them to arrive at receivers distorted, delayed, or not at all. High-frequency radio communication, which depends on ionospheric reflection, is especially vulnerable. Signals that would normally bounce cleanly from the ionosphere back to the ground instead scatter in multiple directions, weakening the received signal and introducing noise. The effect can silence communication links across the polar regions for hours during strong storms. For communities in the far north, where radio remains a vital lifeline, these disruptions are not abstract. They are a tangible consequence of the same forces that light the sky above. The aurora gives with one hand and takes with the other, offering beauty to the eye while stealing clarity from the radio, a reminder that nature's gifts are rarely uncomplicated. Within the turbulent ionosphere beneath an active aurora, the plasma organizes itself into structures of varying size and density. Some of these structures are enormous, stretching hundreds of kilometers. Others are tiny, spanning only meters, yet each one affects the passage of electromagnetic waves through the region. These density irregularities form when electric fields drive plasma flows that compress and rarefy the gas, creating alternating regions of high and low electron concentration. The structures can persist for minutes or hours, depending on the energy driving them, and they evolve as the auroral display changes overhead. For scientists, these structures are both a challenge and an opportunity. They disrupt signals and complicate navigation, but they also serve as tracers of the physical processes occurring in the ionosphere, revealing how energy, momentum, and heat are distributed by the aurora's invisible currents. Each structure is a small record of the forces at work above, a density signature left by currents that flow in patterns too fine for any single instrument to fully capture. When the sun sends a powerful burst of plasma toward the Earth, airlines that fly transpolar routes must pay attention. The same geomagnetic storms that brighten the aurora also increase radiation levels at flight altitudes and disrupt the high-frequency radio communication that pilots rely on over the Arctic, where satellite coverage can be limited. Flight planners monitor space weather forecasts continuously, and when the risk exceeds safe thresholds, routes are diverted to lower latitudes where the shielding of the magnetic field is stronger and communication remains reliable. The detours add fuel, time, and cost, but they protect passengers and crew from elevated radiation exposure and ensure that the aircraft remains in contact with ground control throughout the flight. The decision to reroute is never taken lightly. It is the product of decades of research into how the aurora's parent forces affect the technology and biology of high-altitude travel. Every rerouted flight is a quiet acknowledgement that the same beauty visible from the ground carries consequences for those who fly through the energized sky above. Pilots and operators who depend on high-frequency radio for communication over the polar regions know the aurora as more than a visual spectacle. When geomagnetic storms intensify, the ionosphere becomes so disturbed that radio waves traveling through it are absorbed, scattered, or redirected beyond recovery. The once reliable path from transmitter to receiver becomes unpredictable, and voices that were clear moments ago fade into static or silence. The degradation can last from minutes to hours, depending on the severity of the storm, and it affects not only aviation but also maritime and military communication. The physical cause is the same turbulence that makes the aurora shimmer. Irregular densities in the plasma scramble the orderly reflection of radio waves, turning a smooth mirror into a broken mosaic. For those who depend on these signals, the disruption is a tangible reminder that the forces behind the aurora extend far beyond light and color. They reach into the infrastructure of communication itself, silently reshaping the electromagnetic landscape that modern life depends upon, even as the sky above glows with undeniable beauty. The satellites that guide navigation systems orbit far above the ionosphere, sending radio signals downward through the charged layers of the upper atmosphere. Under calm conditions, these signals arrive at receivers on the ground with predictable timing and phase, allowing precise calculation of position. But during auroral disturbances, the small-scale density structures in the ionosphere cause the signals to fluctuate rapidly, a phenomenon called phase scintillation. The phase of the incoming wave jitters as it passes through irregularities, and the receiver struggles to track the changes. The result is a momentary loss of precision that can range from minor positioning errors to complete loss of signal lock. For most users, the effect is brief and barely noticeable, but for applications that demand centimeter-level accuracy, such as surveying, precision agriculture, and scientific measurement, even a small disruption can compromise the work. The aurora, through its invisible influence on the ionosphere, reaches into the technology in our pockets and on our dashboards, gently reminding us that the signals we trust are traveling through a medium shaped by the restless energy of space. When phase scintillation strikes a GPS receiver, the calculated position can drift by meters or more, depending on the severity of the ionospheric disturbance. The errors are usually transient, lasting only seconds or minutes, but they can accumulate in ways that affect activities requiring continuous precision. A surveyor measuring the boundary of a property, an aircraft on a precision approach, or a ship navigating a narrow channel all depend on stable signals that the aurora can briefly undermine. The position errors arise because the receiver uses the precise timing of satellite signals to triangulate its location, and when scintillation distorts those timings, the math produces a slightly wrong answer. Engineers have developed algorithms to mitigate these effects, but during the strongest storms, the disturbances can overwhelm even the best corrections. The phenomenon is a subtle but persistent link between the beauty of the polar sky and the practical challenges of modern navigation. Every aurora, however faint, leaves its imprint on the signals passing through the atmosphere, bending and shifting the invisible beams that help humanity find its way across the surface of the world. In the far north, where the aurora is a regular presence, surveyors have long understood that the sky's beauty can become a professional challenge. Precision measurements depend on stable satellite signals, and when auroral activity disrupts the ionosphere, the accuracy of those measurements can degrade without warning. Experienced surveyors in high-latitude regions build auroral interference into their planning, scheduling critical work during periods of low geomagnetic activity and building extra time into their timelines for when the sky grows restless. Some use dual-frequency GPS receivers that can partially correct for ionospheric effects, while others rely on post-processing techniques that filter out the noise introduced by space weather. The adjustments are routine but essential, a quiet accommodation of the fact that the forces painting the sky overhead are the same forces introducing errors into the instruments below. It is a relationship that surveyors in temperate latitudes rarely consider, but in the Arctic it is part of the rhythm of work, as natural and unavoidable as the cold itself. The clocks aboard navigation satellites are marvels of engineering, keeping time with accuracy measured in billionths of a second. Yet even these instruments can be affected when a geomagnetic storm alters the ionospheric environment through which their signals travel. The changes in electron density cause tiny delays in signal propagation that translate into timing errors at the receiver. These errors are small, often measured in nanoseconds, but in a system where nanoseconds determine meters, even the smallest discrepancy matters. During strong storms, the cumulative effect of these timing shifts can reduce the reliability of positioning, timing, and synchronization services that depend on satellite signals. Financial markets, power grid coordination, and scientific experiments all rely on precise timing derived from satellite clocks, and all are subtly vulnerable to the same geomagnetic forces that light the polar sky. The connection is hidden from view, buried in the architecture of systems that most people never think about. Yet it is there, a gossamer thread linking the aurora's glow to the precision that sustains the modern world. When the sun releases a burst of energetic particles, some of those particles penetrate deep into the Earth's magnetosphere and reach the upper atmosphere above the polar regions. At the altitudes where commercial aircraft fly, the radiation environment can increase measurably during these events. The additional dose is small, far below levels that would pose immediate danger to passengers or crew on a single flight. Yet for pilots and flight attendants who accumulate exposure over years of polar routes, the incremental increase is a factor that aviation authorities take seriously. Radiation monitors aboard aircraft and in orbit track these fluctuations in real time, providing data that informs decisions about routing and flight levels. The same solar energy that creates the aurora also raises the radiation floor above the poles, a hidden companion to the visible light that most people associate with geomagnetic storms. The effect is another reminder that the aurora's parent forces reach beyond beauty into the realm of health and safety, subtly influencing the environment through which millions of travelers pass each year. Around the world, agencies responsible for aviation safety maintain dedicated space weather desks that monitor solar activity, geomagnetic conditions, and ionospheric disturbances around the clock. Their task is to translate the raw data of solar eruptions and magnetic storms into practical guidance for airlines and flight crews operating over the poles. When conditions warrant, they issue advisories that can trigger route changes, altitude adjustments, or communication protocol shifts. The work is quiet and unglamorous, conducted far from the beauty of the aurora itself, yet it is directly connected to the same forces that create the lights. Each advisory is born from the same physics that makes oxygen glow green and nitrogen shimmer blue, translated from the language of electrons and magnetic fields into the practical language of aviation safety. The space weather forecaster and the aurora are linked by the same chain of cause and effect, one watching the numbers while the other paints the sky. Together, they represent the dual nature of the phenomenon, a source of wonder and a force that demands respect. In the remote outposts scattered across the Arctic and Antarctic, researchers keep instruments running that most people never think about. Radiation sensors mounted on rooftops and in open fields measure the flux of energetic particles reaching the ground, providing a continuous record of how much of the sun's violent energy penetrates the atmosphere above the poles. During strong geomagnetic storms, when the aurora blazes overhead and the magnetosphere is compressed by the solar wind, these sensors detect increases in radiation that confirm the models and predictions of space weather science. The data they collect feeds into global networks that track the health of the space environment, contributing to forecasts that protect astronauts, airline passengers, and satellite systems alike. The stations themselves are small and unassuming, their instruments humming quietly while the sky above them dances with color. Yet their measurements carry weight far beyond their modest appearance, connecting the beauty of the aurora to the practical reality of living within the influence of an active star. Not every geomagnetic event produces a spectacular display. Sometimes the disturbance is so mild that the aurora barely registers to the eye, a faint glow on the horizon or a slight enhancement of the background light. Yet even these gentle events can alter the ionosphere enough to affect communication systems. The plasma irregularities they produce may be small, but they are sufficient to scatter radio waves and introduce noise into satellite signals. High-frequency communication links may experience brief periods of reduced quality, and GPS accuracy may dip by a small but measurable amount. The effects are usually too subtle for most people to notice, masked by the error correction built into modern systems. But for operators who depend on the highest levels of reliability, even a slight degradation can matter. The phenomenon underscores a truth about the aurora that its beauty sometimes obscures. The forces behind the lights are always at work, even when the display is invisible, and their influence on the technological environment around the poles is continuous, subtle, and quietly persistent. When energy from the aurora pours into the upper atmosphere, it warms the thin gas above the poles and causes it to expand upward. The heating is immense in temperature but gentle in effect, because the air at those altitudes is so thin that the energy translates into motion rather than the kind of warmth a body could feel. The expansion raises the effective boundary of the atmosphere, pushing gas into regions that are normally occupied by near vacuum. This swelling can be dramatic during strong storms, with the atmosphere rising by tens of kilometers or more in a matter of hours. The process is invisible from the ground, detectable only by instruments aboard satellites that measure the density of the air through which they pass. Yet its consequences are real and immediate, affecting everything from satellite orbits to the propagation of radio waves. The aurora heats the sky, and the sky responds by reaching higher, stretching toward the stars as if trying to touch the source of the energy that warms it. Satellites orbiting just a few hundred kilometers above the surface normally glide through near vacuum, encountering so few gas molecules that their motion is barely impeded. But when auroral heating expands the atmosphere upward, the density at orbital altitude can increase significantly. The satellite suddenly finds itself plowing through more gas than expected, and the friction slows it down, converting orbital energy into heat and gradually lowering its path. Over time, if the drag continues, the satellite descends into denser and denser air until it can no longer maintain its orbit. During particularly strong geomagnetic storms, entire constellations of small satellites have been lost to this effect, their orbits decaying faster than operators could compensate. The invisible hand of the aurora reaches into space and tugs gently but persistently at the machines humanity has placed in orbit. Engineers must account for this force when designing satellites and planning missions, building in fuel reserves for the orbital adjustments that space weather demands. The same energy that paints the sky with beauty can pull a satellite from the heavens. When a powerful geomagnetic storm sends energy flooding into the polar atmosphere, the expansion of the upper air is swift and dramatic. Satellites that were cruising through rarefied gas suddenly encounter a wall of increased density that acts like a brake, slowing them with every orbit. The effect compounds over time. Each pass through the expanded atmosphere removes a little more energy, lowering the orbit slightly and bringing the satellite into even denser air on the next pass. The feedback loop can accelerate rapidly during prolonged storms, and operators must respond by firing thrusters to boost the orbit back to a safe altitude. For satellites without fuel or propulsion, the outcome is inevitable. The orbit decays until the satellite re-enters the atmosphere and burns up. The loss of dozens of SpaceX Starlink satellites during a geomagnetic storm in early 2022 demonstrated how quickly this process can unfold. The aurora, in its fierce beauty, had reached beyond light and into the machinery of space, reminding engineers that the sky is not passive but alive with forces that can reshape the paths of human creations. When the aurora deposits energy into the upper atmosphere, the heating is not uniform. It occurs in patches and bands that correspond to the arcs and curtains of the visible display. This uneven heating creates pressure differences in the air, and those differences generate waves that propagate outward through the atmosphere like ripples from a stone dropped into a still pond. These atmospheric gravity waves, not to be confused with gravitational waves from astrophysics, travel horizontally and vertically, carrying energy far from the polar regions where they were born. They can influence wind patterns, temperature distributions, and the behavior of the ionosphere at distances of thousands of kilometers from the aurora itself. The waves are invisible, detected only by sensitive instruments aboard satellites and weather balloons. Yet their presence connects the aurora to the broader atmospheric system, showing that the lights above the poles are not isolated events but drivers of change that ripple through the planet's air. Each burst of auroral color sends a tremor through the atmosphere, a whisper of energy that travels far beyond the reach of the light. The atmospheric gravity waves born beneath the aurora do not remain confined to high latitudes. They travel outward and downward, crossing into temperate and even tropical regions as they spread through the layers of the atmosphere. By the time they reach lower latitudes, they have weakened considerably, but sensitive instruments can still detect their passage as faint oscillations in pressure, temperature, and wind speed. The waves carry the signature of the polar storm with them, delivering a diluted echo of the auroral energy into skies that never see the lights. This far-reaching influence means that a geomagnetic storm over the Arctic can subtly affect weather patterns and atmospheric conditions thousands of kilometers to the south. The connection is too faint to influence daily forecasts, but it is measurable and scientifically significant. It reveals the aurora as a phenomenon whose effects extend far beyond the visible display, threading through the atmosphere like a long, slow note that resonates across the entire planet. The lights may shine only at the poles, but their influence touches air that every person on Earth breathes. When energetic particles crash into the upper atmosphere, they do more than create light. They break apart the molecular bonds of nitrogen and oxygen, allowing the atoms to recombine in new ways. One of the most important products of this chemistry is nitric oxide, a reactive gas that plays a critical role in the balance of the atmosphere above. During strong auroral events, the production of nitric oxide surges, flooding the mesosphere and upper stratosphere with a compound that would not otherwise be present in such quantities. The gas is invisible and odorless, yet its chemical effects are profound. It acts as a catalyst in reactions that influence the concentration of ozone and the absorption of ultraviolet radiation. The aurora, through its violent collisions, becomes a chemical factory in the sky, manufacturing a substance that can alter the behavior of the atmosphere for weeks after the visible light has faded. Each storm leaves a chemical legacy, a quiet after effect that outlasts the beauty and continues to shape the air long after the last green curtain has dissolved into darkness. The nitric oxide produced during auroral storms does not remain at the altitude where it was created. Over days and weeks, it drifts downward through the atmosphere, carried by circulation patterns and gravity into the stratosphere and even the upper troposphere. As it descends, it encounters higher concentrations of ozone and begins to participate in chemical cycles that break ozone molecules apart. The effect is temporary and localized, but during prolonged periods of high solar activity, the cumulative impact can become measurable on a regional scale. Scientists have traced the descent of auroral nitric oxide using satellite instruments that detect its infrared signature, watching as the gas slowly sinks from the thermosphere into the layers below. The process reveals a direct chemical connection between space weather and the atmosphere that shields life from ultraviolet radiation. Each molecule of nitric oxide that reaches the stratosphere carries the memory of its violent birth in the auroral zone, a traveler from the edge of space whose journey ends in the chemistry of the air that protects the world. The lowest layer of the ionosphere, called the D layer, normally exists only during the day, ionized by solar ultraviolet light and disappearing after sunset. But during strong auroral disturbances, energetic particles penetrate deep enough to ionize the D layer even at night, creating a region of enhanced electron density that would not otherwise exist in darkness. This nighttime D layer absorbs high-frequency radio waves that would normally pass through, creating a radio blackout that can silence communication over the polar regions. The effect is temporary, lasting only as long as the storm continues, but it can be disruptive enough to force the rerouting of aircraft and the suspension of certain radio operations. The D-layer enhancement is yet another hidden consequence of the aurora, a change in the invisible architecture of the atmosphere that affects the practical world below. The same energy that makes the sky glow also reshapes the electromagnetic environment through which our signals travel, quietly adding another layer to the complex relationship between beauty and consequence that defines the auroral phenomenon. When auroral energy floods into the ionosphere, it increases the number of free electrons and ions in the gas, raising its electrical conductivity. A more conductive ionosphere can carry stronger currents, which in turn amplify the magnetic disturbances felt on the ground. The process creates a feedback loop. Energy from space ionizes the atmosphere, the increased ionization allows more current to flow, and the stronger currents deposit more energy into the gas, ionizing it further. This amplification is what allows the aurora to reach such extraordinary brightness during major storms. The enhanced conductivity also changes how the ionosphere responds to electric fields from above. creating channels of current that can extend for thousands of kilometers and influence the geomagnetic field at the surface. The effect is invisible to the eye, but it is central to the physics of the aurora. Without the increased conductivity, the currents that create the light would be weaker, the display dimmer, and the connection between space and Earth less vivid. The ionosphere is not a passive recipient of energy. It is an active participant, amplifying the signal from space and transforming it into the spectacle above. Even when the sun is shining and the sky is blue, charged particles continue to stream into the polar atmosphere along magnetic field lines. They strike oxygen and nitrogen with the same energy as they do at night, producing the same emissions, the same forbidden transitions, the same colors. But the overwhelming brightness of daylight drowns out the faint auroral glow, rendering it invisible to anyone standing on the ground. The aurora does not stop during the day. It merely hides, continuing its quiet performance behind a curtain of solar light. Only instruments aboard satellites, looking down from above the scattering atmosphere, can detect the daytime aurora, revealing it as a permanent feature of the polar sky. The discovery that auroral activity continues around the clock was one of the important insights of the space age. It showed that the electrical circuit connecting the sun to the Earth never truly closes, that the current flows and the atoms glow at every hour. The daytime aurora is a hidden twin of the nighttime display, unseen but never absent, glowing patiently until darkness returns to reveal its light. While most auroral displays peak around magnetic midnight, there is a quieter, less-known form that appears in a very different place on the clock. Near magnetic noon, when a location on the ground is closest to the point where the magnetosphere meets the solar wind head-on, a different kind of aurora can form. These cusp auroras are created by particles that enter the magnetosphere directly through narrow gaps in the magnetic shielding near the subsolar point. The light they produce tends to be redder and more diffuse than the bright green curtains of the nighttime aurora, and it often flickers with irregular patterns that reflect the turbulent conditions at the magnetic boundary. Cusp auroras are difficult to observe because they occur during the day at most latitudes, hidden behind the brightness of the sky. Only at the highest latitudes during winter, when the sun barely rises, can they occasionally be glimpsed. Their existence reveals that the aurora has a daytime personality as well as a nighttime one, and that the magnetosphere's interaction with the solar wind is not limited to the dark side of the planet. Not all auroras are dramatic. Some of the most scientifically interesting displays are also the quietest. Thin arcs of light can form along the auroral oval and hold their position for hours, barely moving, barely changing, like lines drawn in luminous ink across the dark. These stable arcs represent a state of equilibrium in the magnetosphere, a condition where the energy flowing into the atmosphere is steady enough to maintain a continuous glow without the surges and retreats that characterize more active displays. Scientists value these quiet arcs because they provide a baseline against which more dynamic events can be compared. The stability reveals something about the underlying current system, suggesting that the Birkeland currents and electric fields are flowing in a smooth, laminar fashion rather than the turbulent patterns that produce flickering and motion. To the observer, these arcs offer a different kind of beauty. Not the wild spectacle of a substorm, but the calm elegance of a system in balance. They hang in the sky like horizons made of light, steady and patient, reminding us that even the most powerful forces can find a moment of perfect stillness. Within the glow of an active aurora, dark lanes sometimes appear that move with deliberate grace through the light. These black arcs are not shadows cast by something above. They are regions where electric fields actively prevent charged particles from reaching the atmosphere, creating narrow corridors of darkness within the broader display. The electric fields responsible point upward instead of downward, pushing electrons away from the atmosphere rather than accelerating them into it. The result is a negative aurora, a place where the sky is darker than it would be without the influence of the field. Black arcs reveal the complexity of the current systems flowing through the ionosphere, showing that the same forces that create light can also suppress it with equal precision. They move and shift with the broader display, maintaining their darkness even as the surrounding light changes. For scientists, black arcs are valuable indicators of how electric potential is distributed along magnetic field lines. For observers, they are an eerie and beautiful reminder that absence can be as striking and as meaningful as presence. At every moment of every day, somewhere above the polar regions, charged particles are striking the upper atmosphere and making it glow. The aurora is not an event that begins and ends. It is a continuous process, as permanent as the solar wind that drives it and the magnetic field that shapes it. Even during periods of low solar activity, faint arcs and patches of light persist above the poles, visible to sensitive instruments if not to the human eye. The auroral ovals never disappear. They may shrink and dim, but they remain, tracing the footprint of the magnetosphere's electrical circuit in a glow that has not been interrupted since the Earth first acquired its magnetic field billions of years ago. The permanence of the aurora is one of its most profound qualities. It means that the conversation between the Sun and the Earth has never paused, that the current has never stopped flowing, and that the light has never fully gone out. Somewhere above the world, at this very moment, the sky is shining in a language of color that has spoken without silence since the beginning of the planet's life. On the quietest nights, when the sky above the Arctic seems perfectly dark and the stars burn without competition, the aurora is still there. It exists as a faint, diffuse glow too dim for the eye to catch, a background hum of light that underlies the apparent emptiness. Sensitive cameras can detect this glow, revealing arcs and patches that have no visible counterpart, luminous traces of a system that never fully rests. The faint aurora is powered by the steady trickle of particles that arrives even when the solar wind is calm, a baseline current that sustains the circuit between space and atmosphere at all times. These quiet displays may lack the drama of a substorm, but they carry the same fundamental physics, the same forbidden transitions, the same collisional exchanges between particle and atom. They are the aurora in its most honest form, stripped of spectacle and reduced to essence. A continuous, patient glow that proves the connection between the Sun and the Earth is never truly broken, only sometimes too quiet to see. The aurora is not a decoration hung upon the sky. It is the visible evidence of a relationship that sustains the magnetic balance of our world. Energy flows from the Sun in a ceaseless stream carried on the solar wind across the gulf of space. When it arrives, the Earth's magnetic field receives it, channels it, and transforms it into the light that dances above the poles. The exchange has continued without interruption for billions of years, and it will continue for as long as the Sun burns and the Earth maintains its magnetic heart. The aurora is the signature of this exchange, a luminous record of the energy budget between a star and the planet that orbits within its breath. It connects the physics of the cosmos to the chemistry of the atmosphere, the motion of particles to the stillness of snow, the fire of the sun to the cold of the polar night. In every shimmer and every pulse, the aurora tells us that we are not alone in the dark. We are bound to the universe by threads of light that have been woven into the sky since the very first night the Earth turned its face toward the stars. And so the sky grows quiet again. The currents still flow, the atoms still glow, but the story rests for now. Somewhere above you, invisible wires of electricity hum through the edge of space, carrying the conversation between the Sun and the Earth forward into another moment, another night. You are part of that conversation. Every atom in your body was forged in a star, and the same forces that light the aurora move through the world you rest upon. If you enjoyed this journey, I invite you to like, subscribe, or share a thought below. Now breathe slowly, let the quiet settle. Good night.